So today I will talk about my work titled Novel Architectures for Brain-Inspired Photonic Computers. And I'll start with by giving some background, and after that I'll go over the rest in this overview. So I'd like to start with this presentation with telling you that today we're basically living in the age of the internet. You're probably already aware of this, but indeed, today basically every major aspect of our life can be dealt with online. So this growth in information usage can also clearly be seen in this graph. Oh wait, there's something missing on this graph. I think. So this graph shows the number of exabytes currently being used and projected to be used in the future per month, per year worldwide. So all this data is basically transmitted optically through fiber optic cables, which very often lie on the bottom of the ocean, connecting different continents. And in this figure, each line signifies a fiber optic connection between two data centers, which are the dots on the figure. So the advantage of using light to transmit data is, of course, speed, because you literally transmit data at the speed of light. And also the low loss in optical fibers compared to electrical transmission. So the reason fiber optic cables have so little loss has basically everything to do with a phenomenon called total internal reflection. So I like this figure here, which explains it quite well. When light is traveling through a medium of high refractive index and arrives at an interface with a lower refractive index, like air here, sometimes when the angle is tight enough, all the light gets reflected. So this basically means that you can trap light in a material of higher refractive index. And this is the basic principle behind fiber optic cables, and is the reason why losses are so low during optical data transmission. So most of the data is transmitted optically, but the data processing is still mostly done electronically. And this processing is basically done by high-speed coherent digital signal processors, which translate the optical signals into electronical signals. And then they remove noise and process the signals electronically. So the problem is now that these DSPs are quite expensive and power hungry. So the main challenge is, can we find an alternative for these DSPs? Ideally faster and with less power consumption. So it would be great if we could, for example, make an optical signal processor, because obviously most data transmission is already done in the optical domain. So if we would be able to make such an optical signal processor, we could potentially unleash the same bandwidth benefits for the optical data processing as we have today for the optical data transmission. So this brings us to photonics. Basically, a lot what photonics does relies on building structures to guide and manipulate light on a chip. To then process it or guide it somewhere else. And in our group specifically, we focus on silicon photonics. And the advantage of using silicon is that we can use the same processing techniques which are currently used in electronic chips. And these processing techniques, like CMOS processing, are very, very advanced. So using these techniques makes it a lot easier to pattern the structures you want with very high precision on a chip. So these photonic structures we pattern are often quite simple. They rely on making trenches in a silicon slab, which makes sure that the light cannot escape the structure due to this total internal reflection principle, because the refractive index in silicon is basically higher than the refractive index in the trenches around it. And because the light cannot escape from the sides, it can only go forward, so you basically made a waveguide. You guide the light towards somewhere. And we can make plenty of other structures in materials like silicon. However, the problem is so far that we are not able to make any good transistors like the ones that are being used in electronics. So it makes it quite difficult to do traditional digital computations with an optical chip. So maybe we have to look at a different kind of computer. And this makes us kind of look at our brain. What if we could make an optical chip that functions more like our brain? This is quite interesting because think of what we are good at. For example, speech recognition, facial recognition, driving a car. These are tasks that are traditionally very difficult for a computer. And this means that there's quite some opportunity here to investigate what these brain-inspired architectures can offer us. So the domain of brain-inspired or neuromorphic computing has been getting quite some attention lately, and basically it uses an abstraction of how our brain works. You might know, for example, that our brain consists of neurons interconnected by synapses, and we can make some kind of abstraction of this, where neurons are represented by nodes in a graph, and synapses by interconnections between these nodes. And whenever neurons work closer together, their interconnections become stronger. And when neurons have less to do with each other, their interconnections become weaker. And what we see here is a serious simplification of what's happening in real life, but it might be good enough to solve some tasks that normal computer architectures have troubles with. And the best part is that it's actually quite easily implemented in photonics. With just simple splitters and delay lines, you can make an architecture that resembles this neuromorphic architecture. So this brings us to the main goal of the thesis, which is that we would like to solve telecom-related tasks fast and efficiently, and preferably faster and more efficient than current digital signal processors. And we think that the way forward for this might be to use neuromorphic computing, as competing with electronics with traditional digital computing is just very hard. It's very hard to achieve the same performance. So the rest of this presentation will be structured as follows. First, I'll give a short intro in machine learning. Then we get to the core of my research, which basically consists of 3 different aspects of photonic neuromorphic computing. First, we'll explore neuromorphic computing with signal mixing cavities. And then we'll go to Photontorch, which is a photonic simulator I developed during my PhD. And finally, we'll end the presentation with a short overview of how possibly photorefractive materials could fit into this story. So a lot of machine learning can be reduced to the idea that we want machines, computers, to learn from examples. So I'd like to start this introduction with a classic example, recognizing cats versus dogs. It's something that we as humans are really good at. But how do you explain to a computer the difference between a cat and a dog? You could say, for example, that in general, as you can clearly see in the figures on this slide, dogs tend to be lighter in color. But what do you do when suddenly the computers gets to see a picture of a black dog? Well, you can say one feature is not enough. Maybe dogs have bigger ears or something like that. But what do you do when you then suddenly show this picture to the computer? You see, it's very hard to explain to a computer just by saying the features. So, but I think you can imagine that the more features you add, the easier it is to decide on the difference between them. But who gets to decide on the features? Is it you? Do you tell all the features to the computer? Or ideally, you would like to have the computer find out the features by itself? So we'd rather give the computer just a lot of examples to look at so that it can figure it out by itself what the differences are. But that's a very hard task because computers are really bad at generalizing. And this is what machine learning basically tries to solve in a nutshell. So to summarize, if computers need to learn by themselves, they need to be able to extract the important features by themselves, and they need to use these features to correctly classify each example. And that's exactly how these artificial neural networks tend to work. For example, in the case of the cat versus dog, each pixel is sent through the artificial neural network, and some regions in the network become more activated than others. And how much each neuron is activated is then used as a feature for the final classification. And we see in this case, for example, that the neuron for a cat is more activated than the neuron for a dog. So this is basically the principle of what people tend to call deep learning, where many of these layers are stacked in succession of each other, and where each layer basically predicts a more specific feature up until the moment where a single neuron is basically responsible for the complete prediction, like here, the cat neuron. And this is very successful in practice because this deep learning is, for example, it's very good at image recognition and the derivatives thereof, for example, facial recognition and so on. But the network in the previous slide is not the only story. So, for example, what do we want to do if we want to recognize time-dependent data? Well, if we want to solve tasks like speech recognition, time series prediction, robot control, autonomous driving, or actually basically any telecom-related task, you need some kind of feedback in your system. Because if there's no feedback in the system, the signals at different times cannot mingle with each other. So basically, this kind of network does not have a notion of time, while this one should have some kind of notion of time. This means that we need a special kind of network, and this kind of network we call a recurrent neural network. But the problem with this kind of networks is that it is harder to optimize. It's harder to find a network that kind of makes the right predictions, and it's harder to optimize it correctly. And in the early 2000s, when optimization techniques were not as well developed as now, and when computing power was still a fraction of what it is today, machine learning researchers found an ingenious solution to this problem. And that was basically like, let's not optimize anything that has feedback. And this is basically the definition of reservoir computing. Reservoir computing basically offers a workaround for this optimization problem. And we say that everything with feedback in it is called the reservoir. So this part is called the reservoir. And the reservoir basically acts as a random feature extractor of the data. And then a simple linear classifier is optimized. So this is basically the only part in reservoir computing which is optimized. And this idea is quite nice because it has a very nice separation between the feature extraction, which is done by the reservoir, and the classification, which is done by the readout. And it's important to note. It's important to note, however, that this is a solution from the early 2000s. Nowadays, computing power, optimization methods, and neural network architectures have evolved so much that optimizing recurrent structures has become a lot easier. And this is something that we'll come back to when we discuss the Photontorch simulator. But for now, we'll stick to the reservoir computing approach. So it's worth focusing a bit more on this reservoir computing, because in photonics, for example, such a reservoir is actually quite easily implemented. It's just implemented by using delay lines and waveguide splitters and combiners to make like the simplest possible reservoir, which we call a passive reservoir. And these reservoirs are then used to recognize certain patterns in a bit stream. So you don't recognize cats, but you use it to recognize patterns in a bit stream. So basically, a stream of bits is sent through the reservoir, and some of the nodes are then measured out, and then the measured out signal is then sent to the readout, which makes a linear combination, and hopefully you can do something with this to better solve a certain task. However, it's not, so this works actually quite well. This is something that in 2014, they did some basic benchmark tasks, and yeah, it works actually quite well. But there's a few problems with this kind of design. First of all, it's quite large because implementing such a reservoir quickly takes up to a few millimeters in chip real estate, basically. And for its large size, it still has a quite limited number of nodes. So that means that the computing power of the reservoir is still quite limited. And these nodes also have a quite limited interconnection topology. Each node is only connected to its neighbors, but not to other nodes. So it still has some limitations. So this brings us to the explanation, basically, of the title of my research, which, even though we have indications that reservoir computing in photonics works quite well, the goal of my research was actually to go beyond reservoir computing. So one direction that has been explored was the use of photonic cavities for traditional reservoir computing. So cavities allow for a much more continuous mixing between the inputs compared to a traditional reservoir computer. And where the nodes are basically interconnected. Another way we try to go beyond reservoir computing is to use modern day optimization techniques to basically optimize the reservoir. This is basically a little bit going a bit against the reservoir computing philosophy, but now with current computing power and current optimization techniques and help from machine learning, we can do this. And finally, we'll look into a sort of kind of combination of both, where we'll try to optimize cavities for reservoir computing. And to make this happen, we'll look into a nonlinear effect called the Photorefractive effect, which will introduce some plasticity in the cavity. So, as mentioned, now we'll go into like the core of what I've done during my PhD. So in this part, we'll explore how we can use these photonic cavities to basically go beyond the traditional node-based approach from of reservoir computing. And to that, we need to recall that the reservoir computing can basically be summarized by the following 2 points. It needs to pre-process the input to a higher dimensional space. So it basically needs to do a random feature extraction. And on top of that, it needs to have sufficient memory because the readout doesn't have any memory. And if you have these 2 properties, basically, it means that anything can be used as a reservoir. And to drive this point home, I always give the example of a bucket of water, which has been used for speech recognition by just observing the wave profiles your voice makes when talking. And it's this principle that we like to use for our photonic reservoir as well. Much like the bucket of water, we'd like to send a light in a cavity, and which then is free to mix with itself. However, because we're not able to observe the wave patterns in the light itself, we make it a leaky cavity. And instead of observing the wave profiles, we'll just observe the light that leaks out of the cavity, much like a leaky bucket of water, if you will. And then it works exactly the same as we've done before. The leaky cavity works as a feature extractor for the signal coming in, and the readout is trained on the signal. So first we try to simulate such cavities. So to simulate these cavities, we ideally send a whole bit stream through. However, sending a single bit in simulation through a cavity like this can take up to 24 hours. So that would be very inefficient. So there we did some kind of workaround for the simulations. So one way around this is to coherently superimpose the pulse response of a single bit. So you basically send one bit through, you record how it looks out, and then you add them as according to the bit sequence that you sent in. So this is explained in this figure. You send a single pulse in, you get a raw pulse response for this bit out. Then you use a pseudo-random bit sequence to generate the response of a full bit stream, and then you detect it with a detector model and send it through the readout. And what we're trying to do with this reservoir are basically telecom benchmark operations. One of these operations is, for example, the AND of 2 bits, where 2 subsequent bits in a bit stream are taken. And then the reservoir computer has to output a pulse only when 2 subsequent bits in a bit stream are 1. So for example, here you have 2 subsequent bits in the bit stream and you have to output 1 then. However, the AND task is sometimes a bit too easy. So a more interesting task is the exclusive OR, or the XOR task, where the reservoir has to output a pulse when the current bit or the previous bit is 1, but not when they're both 1 at the same time. So this is a more interesting task, as the XOR operation is a so-called universal operation. So any bit operation can be made by combining different XORs in different ways. So this means if your reservoir is able to do an XOR operation, it can probably do a lot more as well. So it's quite a nice benchmark task. It's also a more difficult task than the AND task, as you really need the pre-processing from the reservoir to a higher dimensional feature space. Even in 2 dimensions, you cannot find a linear classifier that finds it. So how this actually works is as follows. You send a bit stream in through one of the arms of this cavity, and then you record what comes out at each of the 6 other arms. For example, here are 2 outputs visualized according to the input signal that was sent in. And then the measured bit streams are summed up in a readout operation to kind of follow the target exclusive OR. And as you can see, the predicted stream follows the XOR target quite well. And how well is as shown in this figure. So we see that between 25 gigabits per second and 67 gigabits per second, we can basically have perfect performance for the amount of bits we sent through. So we sent in 10 to the 5 bits, which basically only allows us to reduce the error to 10 to the minus 3. If we would want to show a lower error, we should have to send more bits through, but it already takes enough time like this. And the nice thing we have in this simulation is that we can clearly see the different clusters, different subsequent bits create. So here you can clearly see that a simple linear readout can see the difference between the different clusters. So a simple linear readout is enough to perform the XOR task after it was sent through this cavity. Another Telecom task is the header recognition task, where we try to find headers of a certain length in a bit stream. For example, here we visualize the 101 header, so we should only output a pulse when there's a 101 header. Otherwise, we always have to output 0. Headers are typically used as identifiers for a bit stream. So it's basically telling the router, careful, there's some information coming. So this is quite interesting if you can recognize headers like this. So when we do the header recognition task, we see that we can, in simulation at least, recognize up to 6 headers of length 6. So we can go to 6-bit headers. We also see, like, for example, for 3-bit headers, quite nice separation here. And so these are all quite promising results. So this gave us the motivation to actually go fabricate these cavities. And yeah, as the photonics guys under us probably saw, these are photonic crystal cavities. Without going into too much detail, they are very hard to fabricate. And this is also what you see here. We had quite high losses in these cavities, up to minus 60 dB, so they were basically not usable. I think we don't really have the know-how in our research group to make them quite well, these cavities. Or maybe there was a design mistake here. We'll see. We'll never know. But in the end, we transitioned to more easily fabricated cavities. And these cavities, although they also have some quite considerable losses, it's losses that we can manage. They only have like up to 30 dB loss, basically. And the difference between these cavities, well, I'll go back to the previous slide, is that they are just etched in the silicon, much like you etch silicon waveguides, basically. So how do we measure this? We basically generate light in a laser. This light is going through an optical fiber and then sent through a modulator. This modulator is driven by an arbitrary waveform generator. So you basically put the bits here on your optical signal. And then the optical signal is sent through an amplifier. Amplifier goes to the chip. And then here you see the optical fiber arriving on the chip, and it does its thing on the chip. So it goes through the cavity on the chip, and then it leaves the chip again along this optical fiber. Then the light is sent, is going through a second amplifier, and then back into the real-time oscilloscope. Unfortunately, the second amplifier only had like an amplification of 5 dB instead of up to 20 dB, so it was a bit broken. So that means that the signal-to-noise ratio on the measured signals is a bit too high. So yeah, that's what we will get into later. So if you zoom in even more on the chip, you see you have like 4 different cavities that we made. The 100 micrometer diameter cavity up to 500 micrometer diameter cavity. And each, this is, for example, a microscope image of how this cavity looks under a microscope. And each of these cavities has a different response. So for example, if you send a pulse through these cavities, you see that the bigger cavities retain the light a bit longer than the smaller cavities, which is exactly what you want, because you want it to mix inside these cavities. What we see here is then the XOR task, measured XOR task. We see here that we have up to 20% bit error rate, which is really high for telecom applications. So, but a lot of this can be attributed to the higher signal to noise ratio of the second amplifier. So to compensate this, we averaged 10 bit streams together to arrive at this line. This is obviously something that would not be possible in a final product, but at least it gives us an idea what would happen if a normal signal to noise ratio would have been available. And then we also did the header recognition task. Remember, in simulation, we were able to do up to 6-bit headers. In measurement, the results are not as good as in the simulations. We see that we can do up to 3-bit headers for most of the cavities. But once we go to 4-bit headers, yeah, things start to break down. Yeah, so a lot of these worse performance can probably be attributed to still quite high losses in these cavities, because in the end you're just etching some stuff away. Using photonic crystals would be better, but then we should have to figure out how to actually make them in our labs. Yeah, so this basically introduced the cavities. So now I'll go over to something completely different. We have explored cavities as a direction to go beyond traditional photonic reservoir computing, but in the end, it was still reservoir computing. In the end, the reservoir, cavity or not, it was not being optimized. So what if we want to do something that goes a bit further? We want to optimize photonic circuits themselves. We want to optimize the reservoir itself. So this is what we're going to explore in this part of the presentation. We're going to discuss a photonic simulator I developed, which optimizes photonic circuits, just like how neural networks are optimized in software. And this basically gives us the ability to create any neuromorphic architecture, and by extension, actually any photonic circuit, and optimize it as if it was a neural network. And this allows us to go truly beyond the traditional reservoir computing approach. And therefore, it may be a good question to first stand still by how neural networks are actually optimized in practice. And we already know that neurons that fire, yeah. So basically, you say that neurons that fire together, wire together, and you want to emulate this in a in an artificial neural network. And but how do you translate this to a computer language? So the way you do this in practice has actually not so much to do with how it is implemented in how it works in biologically speaking. What we do in normal machine learning and neural networks and deep learning, for example, is we quantify the error the prediction makes, and then the quantity, so this quantity that does that is called the loss. Like, for example, at this figure here, where we try to fit a line through a bunch of data points, the red line fits the data points not so good as the other line, so it has a higher loss, and the yellow line has a better loss, and then the green line is the optimal line through these points. So the loss for this specific example can be reduced by changing the angle of the line, which is basically very easy. But the angle of the line is just a single parameter. What if you have a whole network of parameters to optimize? Well, the principle basically remains the same. First, we quantify the error, and then we use an algorithm called backpropagation um, to optimize each parameter in the network according to the prediction the prediction error the network makes. So, for example, the network predicts a cat with 60% certainty. This means that the neuron responsible for the cat prediction makes a 40% error. And this error will then be partitioned between the neurons in the previous layer. Each will get a part of it, and this will optimize all the parameters in the circuit from the back to the front. So this is what it means to do backpropagation. And this is an iterative process, as clearly, So this is an iterative process, as basically the error is continuously updated by showing new examples to the circuit until like a minimum of the loss function is found. So why wouldn't we be able to do something similar with photonic circuits? After all, optimization techniques have improved a lot since the invention of reservoir computing in the early 2000s, and keeping the parameters inside the circuit fixed is maybe not necessary anymore. However, using backpropagation to optimize physical parameters of a photonic circuit is not so straightforward. Backpropagation is not something you can just slap onto an existing photonic simulator, because it's very important to know the order of mathematical operations that happened, and because only then you can correctly apply the algorithm. And no photonic simulator to date keeps actually track of the operations for you. So this basically implies that a whole new simulator needs to be built up from the ground up so that it keeps track of the order of operations and so on. However, luckily, we can stand on the shoulders of giants here and use the countless hours of machine learning research to our advantage. And we can use one of the many well-established machine learning libraries like Pytorch to help us take care of the tracking of the order of operations and so on. And this is what we did. We basically re-implemented parts of the Café photonic simulator from scratch to obtain a simulator which I call Photontorch. And this is a simulator which is basically able to optimize any photonic circuit using backpropagation. So any photonic circuit, so not only neuromorphic structures. So how this simulator can, for example, be used is during the optimization of a photonic reservoir. So what you've seen here is the swirl reservoir we saw earlier during my introduction. And basically this reservoir is basically like the grandfather of the optical reservoirs, of the on-chip photonic reservoirs, and it can perform the XOR task quite well, as you can see here. However, like in standard reservoir computing, the internals of this reservoir are not optimized, and only the readout is. So when the readout is iteratively optimized, we get the following learning curve, which describes well how well the output of the system follows the target function. So this is basically how well the output of the function describes the target. And what we see is quite cool, because if we simulate this same circuit with Photontorch and we allow some phases of the reservoir to be optimized, basically better performance can be achieved. And it is also achieved faster after less training steps. So this is what you see here with the red line. And moreover, since we can now backpropagate through the circuit, we are able to basically cascade two of these reservoirs together. And this is something that previously was totally impossible, as basically the action of this last reservoir cannot be inverted, and the intermediate weights of the cascadian could not be found. But it is actually quite easily done with the Photontorch simulator. So you see here that the blue line is the performance of a single reservoir where only the readout is optimized, and the yellow line is the performance of the cascaded reservoir. You also see it reaches the good performance faster, and yeah, it also gets better performance in the end. However, that's not really everything the Photontorch simulator can do. As mentioned, it can also optimize totally different architectures. For example, here we simulated a unitary recurrent neural network, and this is quite different architecture than the traditional reservoir architecture, and has a lot of parameters to optimize. For example, this consists of 384 MZIs, each of which have 2 parameters to optimize, and all of them are optimized simultaneously. And what we can do with this circuit is recognize digits, which are sent pixel by pixel through the network according to like a fixed randomized permutation. And yeah, so, and with this network, we can basically achieve, we can basically match the world record on accuracy on this pixel per muted digit recognition task. So it's important to note that this is mostly a showcase of how Photontorch is able to optimize large circuits with many parameters. But a lot of approximations have been made to make this work. So implementing it in photonics is definitely not yet feasible. However, that does not mean that people are not allowed to try to make these things. Here's, for example, a 4x4 thing, that mesh circuit that was fabricated in MIT in 2017. It's a long way off of the 128 by 128 that was used in simulation of this MNIST task. But at least it allowed the spin-off of 2 different MIT spin-offs, like light intelligence and light matter, if I'm not mistaken. So, however, as I mentioned before, you're not limited to neuromorphic architectures. Also, pretty normal photonic architectures can easily be optimized with Photontorch. So here you see, for example, a coupled resonator optical waveguide, or what we call a CRO, which is optimized in the frequency domain to basically create a bandpass filter. Or you can also basically, and here you see a mesh network that was optimized to compensate for variability in the components. So for example, you have a component which you cannot completely control because of maybe temperature variations or fabrication variations. So let's say it has like a 5% error. By putting them in a mesh like this and optimizing it well, you can optimize up to, you can reduce the variability in the complete component. So you go from 5% error, or 5 and standard deviation of 0.05 to a standard deviation of 0.016. And yeah, so of course, this needs way more chip real estate and is also quite difficult to fabricate because it's a lot bigger, but it's a quite nice idea, at least, to explore. So yeah, so you might wonder, why is it actually that Photontorch is able to optimize photonic circuits as if they are neural networks? So this has everything to do with how it is implemented under the hood. So as you may know, any photonic component can be represented by a scattering matrix, like here. And these scattering matrices can be reduced to like one single circuit scattering matrix. And the S matrix of the circuit is applied every time step to the fields going through the circuit. So this resembles a lot a weight matrix, which is applied over and over every time step, like is the case in recurrent neural networks. However, this has to be noted that this is an approximation, as ideally you need to take the Fourier transform of your S matrix to have a complete accurate approximation of a complete accurate prediction of how your circuit acts in the time domain. And this leads to methods like vector fitting, which create an infinite impulse response method, or finite impulse responses, like which are used by simulators like interconnect and so on. So these things, to be clear, they can also be implemented in Photontorch. Then you go to like nonlinear components and so on. But the nice thing about using this approximation, which is shown here, where you basically use the frequency domain S matrix with a delay, is that it is very parallelizable. So you can basically do the simulations very fast and efficiently on a GPU, graphical processing unit. And this is what you see here in this graph, where we where we calculate the both frequency domain responses and time domain responses of the graphs. So especially this figure is quite interesting. This is the time domain response of coupled resonator optical waveguide, where you use multiple wavelengths at the same time and multiple waveforms at the same time, and you see that the GPU performance stays more or less flat, while the CPU performance goes through the roof here. So this is what is possible with this approach, or this parallelization approach. So if you're interested in simulating non-dispersive, and I realized that using a CRO as a performance metric was maybe not the best choice in this regard, circuits for multiple wavelengths and multiple input waveforms, then Photontorch is a quite good choice. So, so far we've discussed cavities as reservoir computers, and then we established that with modern optimization techniques, we can go beyond reservoir computing, and we use these techniques to, among other things, optimize the internals of a photonic reservoir. So this basically begs the question if we could somehow combine these two ideas. Can we optimize the internals of a cavity? Well, not with the cavities on chip we have discussed earlier, because they are built of silicon, and yeah, it's quite hard to optimize a continuous slab of silicon. But maybe we can use a different kind of cavity, and this is what we'll explore in the final part of this presentation. So before we start this part, it's maybe important to recall that light, as you may know, is an electromagnetic wave. So and the cool thing is that electromagnetic waves interfere just like normal ripples on a pond and interfere. So when waves interfere, you get regions of high intensity and regions of low intensity, where there are almost no waves. So if you indicate the regions of high intensity here, as it's like this. So you can do the same basically with two laser beams. When you let two laser beams go through each other, they will interfere and get regions of high light intensity and low light intensity. And when you let them interfere in a photorefractive crystal, something really interesting happens. First of all, the light excites electrons in the material. So the electrons will now be free to diffuse through the crystal. And generally speaking, they will move away from the light. So because they are excited at the high intensity regions, they will move away to the low intensity regions. And then at the regions of low intensity, they will get trapped again because of some recombination of the carriers. So basically you get regions where you have positive charges and regions where you have negative charges. So this basically creates creates an electric field in the crystal. So, and this electric field is basically constant, because if you remove the light, the charges are trapped. So this is there to stay, this electric field. And this electric field is what we call the space charge field of the photorefractive crystal. But the photorefractive crystals have one last property that's quite interesting. They exhibit what we call the Pockels effect. So that means that the optical properties of the crystal change with the electric field that's present. So this means that the refractive index will change according to what we call the Pockels effect. So what you end up with is a refractive index grating, which is moved a quarter period with the respect of the interference pattern. And you basically create like this a grating in your crystal. And this effect has been studied a lot, and it's basically the underlying principle behind holography and so on. So now we'd like to simulate this effect. And for this, I worked on another simulator, basically an FDTD simulator, so finite difference time domain simulator. It's a kind of simulator for electromagnetic effects, where these governing equations for the photorefractive effect were basically integrated into. And what we see is that indeed we can accurately simulate the effect, as I just explained. Moreover, since the light basically creates a changing refractive index pattern, this pattern will start to influence the propagation of the light itself. So this is quite interesting. If you stop one of the laser beams after a while and just let the laser beam on the left take over, it won't go straight through the crystal, but it will be reflected by the grating you just created. And this is an effect called beam coupling in photorefractive crystals. So this beam coupling effect is actually quite interesting, as it's kind of inspired us to see what would happen if you let different bit streams interfere. For example, when you let two identical bit streams interfere, you'll get a grating here, for example. If you let two alternating bit streams interfere, yeah, you basically get a non-interfering pattern. And if you let two random bit streams interfere, then you get like a combination of both. And you can say, yes, that's all very logical, of course, but actually, maybe that's an effect that can be exploited for photonic neuromorphic computing. Imagine for a second that you place, for example, such a photorefractive crystal inside a cavity. And now we send a bit stream through the cavity. And because it's a cavity, the signal will take a few round trips through the crystal before it's measured by the camera. So this means that bits at different time periods will start to interfere inside the crystal. So basically, different bit patterns will start to interfere, creating different gratings in the crystal. Basically, different regions of the crystal will get activated by different bit patterns. And this sounds very familiar to how the brain works in a very hand-wavy way. as just like the crystal, different regions of the brain get activated for different observed patterns. So this similarity is something that we wanted to explore. And so what we did is the following. We first simulated this photorefractive cavity and used it for reservoir computing, just like that. And then we simulated the propagation of a very large number of bits through the crystal, which obviously will change the refractive index in the crystal and get like patterns in the crystal. And then we used the reservoir again, just like we did before. And what we see is that we see an improved performance, at least slightly improved performance in this versus this one. So this is a quite interesting result, but it remains obviously a bit philosophical, as a lot of hurdles have to be surpassed to make this such a system in real life. However, it's quite interesting that the simple act of what we call priming such a crystal can have an influence on the future performance as a reservoir computer. So this brings me to the end of my talk, and I want to have, I want to end the talk with kind of these three main takeaways. So first, we explored on-chip cavities, and they seem to have like a promising, they seem to offer a promising alternative for traditional node-based reservoir computers. And we tested them both in simulation and in experiment on header recognition and XOR tasks, and they show promising results. But yeah, especially the measurement results should get some more improvement. And then we went on to the Photontorch simulator, which shows the viability of optimizing photonic circuits through backpropagation. This basically yields a completely new way of optimizing photonic circuits. And on top of that, it's very parallelizable, which makes it very fast for wavelength multiplexing and waveform multiplexing. So basically sending different waveforms at the same time. And then we quickly explored how the self-reorganization in photorefractive crystals, such as, for example, priming the crystal, might help for neuromorphic computing schemes that go also beyond reservoir computing, such as self-learning and so on. So with this, I'll conclude my talk, and I hope you enjoyed it. Thank you very much.